If you have a locked, completely opaque box, how do you figure out what's inside without breaking it open? One way is to tap the outside and listen to the pitch. A hollow box rings differently than one packed with dense material. You're using resonance to map the interior. Early medical imaging relied on X-rays to cast shadows of dense material. In this historical setup, you can see the focus is entirely on the skeleton. Bone shows up clearly, but the brain, the ligaments, and the internal organs are almost entirely absent from the plate. Hydrogen is the key to seeing those softer materials. Since the human body is mostly water, it is saturated with hydrogen atoms. By exploiting their magnetic properties, researchers found they could turn these abundant particles into individual transmitters. Instead of shooting radiation through the body to create a shadow, magnetic resonance imaging makes these internal protons ring. The machine listens to those tiny radio echoes and maps them out to build a detailed, three-dimensional picture of soft tissue. This is the core of a clinical MRI magnet. To start the process, a patient is positioned inside a massive electromagnet. Inside the body, hydrogen protons are normally spinning on their axes, generating their own microscopic magnetic fields. But they are pointed in random directions, acting like a pile of uncoordinated compass needles. This diagram illustrates what happens at the atomic level. When that external magnet is turned on, the random protons are forced into an ordered alignment. They point either parallel or anti-parallel to the field lines. Pointing parallel takes slightly less energy. Because nature prefers the path of least resistance, a few more protons will align parallel than anti-parallel. Across billions of atoms, this creates a net magnetic vector pointing along the length of the machine. This creates a synchronized magnetic baseline. The body's atoms are standing at attention, ready to be manipulated. Now, the machine acts like the mallet striking the box. It sends in a radio frequency, or RF pulse. This is a short burst of energy specifically tuned to disturb the proton's rotation. As the incoming radio wave hits, it tips that vertical magnetic vector over. The protons absorb the energy and begin to spiral in a horizontal, transverse plane. When the machine turns the RF pulse off, the protons relax and stand back up into their original alignment. As they return to that baseline state, they release the energy they just absorbed as a tiny radio signal. Protons in water-dense tissue relax at a different speed than protons in fat. Physicists measure these recovery speeds using two time constants, T1 and T2. By listening to how these radio signals fade, the computer can distinguish between muscle and fluid. These varied relaxation speeds allow the machine to assign different shades of gray to different tissues. We can get a signal out of the body, but millions of protons are broadcasting at the same time. The machine has to identify exactly where a specific echo originated. This chart shows the longitudinal magnetic vector. Gradient coils create varying magnetic strengths, making top protons spin faster. As seen in section C, this creates distinct phases. By shifting gradients across axes, every coordinate gets a unique magnetic signature. What hits the machine's receiver is a mixture of all these radio waves. The computer runs this signal through a mathematical process called a Fourier transformation, which untangles the mixture into individual frequencies. Each frequency corresponds to a specific physical location. The computer quickly calculates the intensity of each echo and matches it to the correct coordinate on a pixel grid. This precision allows doctors to delineate between a benign cyst and a dense tumor, or trace the flow of blood through specific vessels with millimeter accuracy. But this precision comes with physical constraints. These high-voltage danger signs are a reminder that the magnet's pull is constant and powerful, making the room hazardous for metal. The scanner also has to wait for protons to fully relax, which can make imaging slow. To speed things up, fast imaging sequences use smaller flip angles, tilting the protons just 10 to 35 degrees rather than a full 90. This leaves enough baseline magnetization that the machine doesn't have to wait for a full recovery, cutting scan times to seconds. Beyond anatomy, scientists use MR spectroscopy to identify the chemical makeup of tissues. By analyzing specific metabolic signals, doctors can monitor changes in cell physiology without a physical biopsy. These advancements turn the scanner into a tool for monitoring metabolism. Doctors can now track the actual chemical changes occurring inside a living patient without ever needing a physical sample. The process follows a 4-step rhythm. Step 1, the giant magnet aligns your protons. Step 2, a precise radio wave knocks them over. Step 3, as the protons relax and stand back up, they broadcast their own radio signal. Step 4, gradient magnets assign every signal to an exact physical location. This final review illustration shows the ultimate result. We no longer have to guess what's inside the locked container. MRI allows the body's own atoms to broadcast their location and condition.